So even if it was introduced as an algebra colloquium, I will start a little bit more on the combinatorial side, and yeah, later on I will explain how we got to the algebra. So at first I would like to talk about a problem from combinatorics, the Hadwiger-Nelson problem around 1950, and that's a graph theoretic problem. So we consider a graph where the vertices are all the points in R2, and there are some edges. So and when should two points in the plane be connected? This should be the case if and only if the Euclidean distance is exactly equal to 1. This is the graph we would like to consider here. And so the problem is now about coloring the vertices of this graph. So let me fix some notation. I would like to talk about an N coloring of a graph. This should be a map C from the vertices to the numbers of 1 to n, such that when I have two points that are connected, then they must not have the same color. So C of x is not C of y. There's a graph invariant, the chromatic number, chi of d. This is just the minimal number, natural number n, such that there exists an n coloring of G. And so the Hadwiger-Nelson problem is now, what is the chromatic number of this graph over here? So what is chi of G, red G, is this one as above. This is an open problem. So it is known that this one is 5, 6, or 7. Yeah, and I would like to draw a little picture how we can see that we have that the chromatic number has to lie in this range.
Is it an obvious thing that is finite?
Yeah, I will write down the picture for which we see that we can construct a coloring with at most 7 colors. So I probably need some time because I have to draw all the some hexagons. They should be all regular. Yeah. So this is just the usual hexagon tessellation symmetrically. And that's okay. And yeah. So all these hexagons should fit in a circle of radius 1, and all of them obtain color, and there are many colors here, but I think not 7. So yeah. So just to indicate what's happening here. And then this one green and this one is green, and this coloring will be periodic. Sorry. So yellow here. Where else is yellow is also here, and I should add some color here, and this one goes as well there. So when you go 2 up and 1 in the upper left, then you have the same color. And you can extend this periodically. And yeah, since these hexagons are small enough so that they fit in a circle of radius 1, it's okay that all these are colored in the same color.
Radius 1/2 maybe? Because if like I have radius 1, then there might be distance 1 apart.
So radius is 1/2, but that means that this one fits in
I was confused.
Circle of okay, yeah. Yeah. Thank you. Okay, so from this tessellation, we see that it is enough to have 7 colors. Maybe I have 4 colors so far. I just indicate where the other ones are. So here is color 1, 2, 3, 4. This is also 4. We have here another color number 5, color number 6, and here's color number 7. And yeah, as explained before, we just periodically extend this in this way to see.
Not totally clear to me. So how is the?
So we have
maybe because also the colors are not distinguishable enough.
Yeah.
Maybe write the C's.
So oops. 1, 2, 3, 4, 5, 6, 7. So and this one should be 6, 7, 1. This is the same colors here. So here again, color number 2. So here it's just 1, 2, 3, 4, 5, etc. And yeah, there's a shift in this direction. Okay. Yeah. So this is more or less the proof for the upper bound, and yeah, for the lower bound, there is a very old result concerning this direction. This will be again not a very beautiful picture. Just to indicate the idea, we have triangles. Each side of the triangle has length 1, and other triangle sitting over there. Something like this. So if you're interested, you can Google it. This is the German name, Moserspindel. I don't know what Spindel means in English. So from this picture, you can see that you need at most 4 colors. So when we look at this one,
Spinning wheel.
Maybe spinning wheel.
Spinning wheel. I'll look it up.
Yeah, okay. So this point over here is connected to these, and yeah, so they all must have different colors, so you need at least 4 colors.
Is it a regular pentagon?
Um,
Or the outside is a regular pentagon?
No.
Ah,
The
no,
important thing is that
because those
these
are
triangles have to be regular. Yeah. So, from
Spindle. It's a spindle. According to the
this
file.
helps.
okay, it's a helpful thing. Okay, so from this picture, you can see that you need at most 4 colors, and when you put them, lots of them together in a very complicated way, you see that you need at most 5 colors, but
At least.
at least, yeah. This is a construction that depends on this one, but so the easiest construction, the smallest construction where you need almost 5 colors of such a thing contains about 500 vertices. So no, I won't take it down. Yeah, that's the Hadwiger-Nelson problem. And I was looking at this problem from a more general point of view. So here, the definition of this graph, we use the Euclidean distance. And I would like to look at graphs that are built similarly. So instead of just R squared, we look at some arbitrary vector space. Vector space over some field F. And yeah, okay, then we do not have a distance, but let's call this vector space V. And instead of the Euclidean distance, I would like to use a quadratic form. So the Euclidean distance is 1. One moment, please. Is 1 if and only if. This is 1 if and only if x1 minus y1 squared plus x2 this one squared is 1. So what we do here, we now like to consider graphs of the form so G QA.
But can I do something?
Yeah.
Oh, sorry.
So
Yeah.
give me a minute so that I have the definition of the graphs, and then I'm happy to answer some questions. So Q is from V to F, a quadratic form. A is in F, and 2 elements are adjacent in this graph if and only if the different represents this fixed scalar. This is the generalization of the graph we looked at before. So this question was first.
Yeah, I think my question is more or less answered, but we are then looking at finite dimensional vector spaces.
Yeah. Okay.
Yeah, you don't have to write. I was just wondering, it seemed logical to restrict.
Yeah.
But I guess it could be made for infinite dimensional, maybe. I don't know.
Okay.
So how much does this problem actually depends on the metric. I mean, these arguments don't, right? This could be, I mean, instead of triangles, you just take geodesics and geodesic triangles, and then how much? Yeah, it's just a curiosity question.
What?
If you just take a metric on R2,
Yeah.
the chromatic number is independent.
So, of course, the idea here is to find the.
But if those lines are just geodesic, then well, you will need to maybe to put it inside. I don't know. Yeah, I mean, yeah,
So,
inside a ball or something.
So at least the metrics coming from norms are equivalent. So
I think it should kind of depend. You can, for example, take the discrete metric because then any 2 points are connected with an edge. So there, at least there are some things that you should ask of the metric. And I don't even know if being equivalent with this one would work. Like I can imagine that you could make a constellation where you just get the full n graph somewhere, instantly giving you a lower bound on the chromatic number, where all the points are supposedly distance 1 away from each other. I could imagine that happening with rather similar metrics.
Well, just a curiosity.
But question, thank you. Yeah, and yeah, from this point of view, I started to study graphs of this kind coming from any quadratic form. Okay.
I mean, since you fixed the A, why don't you fix it to be 1? Because you can scale your cube by 1 divided by A.
Yeah, that's right, of course, but and I think it depends on the way what you would like to have given. Of course, you can adapt when you are first given a quadratic form, and you the idea was we fix a quadratic form and look at all the graphs that can occur for this quadratic form. So then it may depend on the A. There may be non-isomorphic graphs that occur.
And also can be, it doesn't have to be positive definite or anything, right?
No.
I mean, it can be 0.
No. So just starting from a metric, I considered any quadratic form. And I will give examples of how this behaves in isotropic quadratic forms. Okay. So this is kind of motivation, and yeah, I further looked at some derivative problem. Because yeah, finding the chromatic number is hard. Finding the clique number, which I will now define, is in general also hard, but there's an algebraic description, at least for these kind of graphs, that I will now show. So a clique in a graph is a subset of the vertices such that the 2 elements in C, the different elements, we have that xy is an edge in the graph. So it's a complete subgraph. Omega of G is invariant of the graph. Similarly, at the above is defined as the maximal size of the clique in G. So, and yeah, what's the connection to the chromatic number? We clearly have the chromatic number is at least the clique number. Since, yeah, when I have a clique, assume we have a clique of size 4. All these 4 vertices are connected, so clearly they all have to be colored differently. We would like to have the coloring. So, and thus, in order to gain some knowledge about the chromatic number, one can try to find out something about the clique numbers.
Is the clique number known for this original graph?
Yeah. This is 3. Just take a regular triangle. You in the plane you cannot find the 4th.
Yeah. Right.
Edge. Yeah. So yeah, in fact you spoiled a little bit. So the approach I will not present will not gain anything new for the original graph, unfortunately. Okay, so I would now like to explain how it was possible to compute the clique numbers more or less explicitly in many cases. The first step is we do not have to consider the whole graph. It is enough to consider the following reduced representation graph. So QA representation, and yeah. Okay, what do we consider? Instead of considering all vertices, we just consider the ones that, when evaluated in the quadratic form, we obtain A. And yeah, we take all edges between them that were there before. So we have here just oops, sorry, so this should be the set of subsets of to be read consisting of exactly two elements. So instead of looking at the whole graph, we only look at these. And yeah, why do we do that? We have that the clique number of the original graph is more or less the same as for the reduced graph. Instead of if A is not 0. Okay, let me explain that briefly. The definition of our graph is invariant under translation. So when we have given some clique, we can translate it in a way such that 0 is in the clique, the 0 vector. And yeah, we can omit it. And yeah, depending on whether A is 0 or not, we maybe erase an element of the clique or not. And this is why we have this connection over here. Okay, let's now translate it into algebra. Basically, linear algebra. So most of the stuff could be done by a good student in the first year, more or less. So if you can calculate with bilinear forms, you rarely see a formally. And I have two different elements. Two different vertices in the reduced graph. They are connected if and only if we know that the value of the bilinear form evaluated at these two vectors is A. And yeah.
Wait, sorry, what is B?
So B is the associated bilinear form to Q. So so B of xy is E of x plus y minus P of x minus P of y.
Okay, thank you.
That's a bilinear form since Q is a quadratic form.
What is P2? What do you mean by P2 of the red?
P2? What? The set of subsets of this one with exactly two elements. So edges are subsets of exactly two elements.
I don't. What did happen when going from V to V red? In which sense is this different?
We do not have the whole vector space as vertices, but only those vectors which fulfill this condition.
Okay, yeah.
So when we think in the plane, the graph I mentioned before, instead of looking at the whole plane, we would just look at the unit circle.
And then we obtain a maximal clique really by taking the clique from this reduced space and then adding 0 to it because 0 will be the
Yeah. I will now distinguish between the two cases. But I do not want to talk about too much about the case in which A equals 0, since then one readily sees that maximal cliques are subspaces. Maximal cliques are subspaces. In fact, totally isotropic subspaces. That means, given any vector of this space, when you evaluate it in the quadratic form, I obtain 0. Yeah. So when all the vectors I evaluated to 0 in the subspace is closed under subtraction, and so one value sees that this one gives the clique, and when I can add another vector, I can consider the whole span of the new space. So just yeah, I just wanted to make the point that this is not an interesting case.
I'm not sure whether people know what the totally isotropic subspace is.
Okay.
This is our lingo.
Okay. So maybe that means P of x is 0 for all x in the subspace. So, and yeah, okay, and when you know that, it's okay. Yeah, let me first clear the blackboard before I go on. Any further questions so far?
This is for the original graph that you're saying this maximal cliques are totally isotropic subspace.
Yeah, of course.
So I see why a totally isotropic subspace is a maximal clique, probably. Why the other way around? Should I believe it, or
So
why is a maximal clique necessarily a subspace?
you can just look at the span.
Mm-hmm.
Using this condition for the bilinear form, this is then also 0, if A is 0. And so you see that the span of a clique consisting of isotropic vectors is totally isotropic subspace than a clique.
Are like these all isomorphic? The totally isotropic subspaces?
For a quadratic form, indeed,
Yeah.
this is they are all of the same dimension. This is not trivial.
Yeah.
Okay.
Yeah. So in quadratic form theory, the size of a maximal totally isotropic subspace is important invariant. It's the bit index of quadratic form. So in this case, you can state the clique number in terms of this invariant of the quadratic form.
Yeah. Okay. Thank you.
So yeah, we'll continue to work with subspaces. So when we are given a clique C in the reduced graph, and I have some elements in there, at least 2 of them. We would like now to consider the span of these vectors. So we have a lot of linear conditions so far. We have this one over here, this lemma. We have the values of the quadratic form, and putting all that together, we obtain a system of linear equations which tells us which other vectors in V can be added to C.
So the clique problem is trivial in that case, but the coloring is not.
No.
Yeah.
It's
only
still not.
one, but okay.
Yeah. So we can determine the other possible vectors. Vectors in W that may be added to our given clique. So here, of course, it's not a maximal clique in general. And yeah, in fact, these are not very much. There's at most one vector that we can add to a clique. When we are given those. We have. So let me write that down. So we can look at the characteristic of our field. If it does not divide the number n here, plus 2, then we cannot add anything. And otherwise, we can add the negative to the sum of all these xi. Note that I did not talk about linear independence. That works out in this case as well. So even when the xi are linear dependent and are clique, then this condition also works just by canceling out some of this. Yeah, so yeah, this means we just to consider to calculate the clique number, we have to look for subspaces such that I've given the basis. Let me write it down. So we are just looking for a subspace with the basis let's call it yeah, x1 to xm such that Q of xi is a and B of xi xj is also a for all I not equal to j. Yes, please.
So when you say this sentence, what you mean is that if we have such bases, we have like the clique number is m.
Mm-hmm.
Yeah.
So yeah, depending on the characteristic. So
yeah,
maybe we can add another element, and since we have a not 0, we can add the 0 vector.
Yeah.
So,
okay.
So the problem is now linear algebra. Search for such a subspace, and from the dimension of the subspace, yeah, adding 1 if this holds, and clearly adding another 1 for this condition.
Okay. Yeah. Thank you.
Yeah. So okay. Now we can work purely algebraic in these cases. So the quadratic form on this space is then unity determined. Yeah, it's associated bilinear form. Let me write down the Graham matrix. Bilinear form has Graham matrix. So I will denote that by AK, it's just A times the identity of the appropriate size. In JK, this is a matrix consisting only of ones. Let me write down an example of a field of characteristic 0. This looks as follows. This is just a quadratic form that I should not try. So a k-dimensional vector with entries a1 to ak is then mapped to 2 times 1 times a1 squared plus 2 times 2 times 3 times a2 squared and so on. So it really is can be computed explicitly. Squared.
No, I can.
So I would now like to look at some explicit fields. And let's first start with the real numbers. So for the real numbers, sorry, there should be some A in it. Shouldn't it? Oh, yeah. Yeah, sorry, I forgot the factor A over here. Okay, so for the real numbers, all the coefficients here are positive. So this form will be definite. It's positive definite if and only if A is positive, and negative if and only if A is negative. And so we will see what you've assumed just at the beginning of the talk. So given a quadratic form over the reals, from linear algebra we know it is unity determined by its signature. That's Sylvester's law of inertia. So we can diagonalize this quadratic form, respectively, it's associated by linear form. And we can count how many positive entries are on the diagonal, how many negatives on the diagonal. And yeah, we would like to find a subform of this form So this is, maybe I wrote down the signature. So in this case, it is signature K0, in this case 0K, just depending on the sign of A. And so we now have to look how big can we make the K to fit it in here. And that's how we can solve the clique problem over the reals. Oh, sorry, this one should have obtained an index. This depends on A and K. I'm sorry. So you can write so QAK is a subform if and only if, yeah, two cases. K is at least R plus, if A is positive, or R minus, if A is negative. So coming back to the Euclidean plane, what does that mean? So we have this unit circle. The Euclidean distance is a positive definite form. So we have signature 2, 0. This form for k equals 2 is also a positive definite form. It's therefore just isometric to the Euclidean, to the quadratic form over here. So we can choose k equal to 2. We can thus find two vectors on the unit circle whose difference should be 1. And to complete it to maximal clique, since we do not only consider the reduced graph, but want to consider the whole graph, we add the 0 vector. So these are our ones. And yeah, our intuition was right. This is, in fact, a maximal clique in this case. Yes, so more or less continue from the point I finished before the break. And yeah, we handled the reals. And now we consider the field of rational numbers. And yeah, we can state a global principle for the clique numbers in this case. So if we are given a quadratic form over Q of fix the dimension and an A in Q, so there's a famous local global principle in quadratic form theory from Marcinkowski. We can go from the PQ to p-adic numbers. So let me define this integer m. This should be the maximum of q such k such that QAK is a subform of Q in the sense I only talked informally about before. And this is exactly using this principle from Minkowski. Here, the bit index, the invariant we mentioned before, measuring the size of a maximal totally isotropic subspace. QAK. So we add to form we consider and our test forms with a negative sign and look at it for the p-adic integers. This should be at least k, this minimum. So what does that mean? What does it tell us? So this means we would like to compute the clique numbers.
Sorry, what is the statement of the theorem? Is the second equality? Is the equality?
Yeah, this is here. So just wanted to explain. It's just a relation over the rationals, and we can reduce it to a lot of relations over the p-adic fields. So we have to look at each p-adic field. We can consider our quadratic forms as forms of the p-adics. Here the quadratic form theory is much easier. So this can be solved with many case distinctions I do not want to put on the blackboard. Yeah, that's the way how this can be solved over the rationals. In fact, the quadratic form theory over the p-adic integers relies heavily on the quadratic form theory over finite fields. And yeah, over finite fields, the problem is relatively easy. So we'd like to also study the problem over finite fields. If you don't mind, do not write down the explicit solution, but I only write down the solution can be given in terms of the dimension of our quadratic form, the determinant of the quadratic form, and yeah, the characteristic, the positive characteristic in this case. So there's a tabular 5 cases, and yeah, it's not that difficult to write that down in all these different cases.
But and by dimension, you mean the rank?
Yeah, the dimension of the underlying vector space on which the quadratic form is defined.
Ah.
So this is the dimension. The Q is the quadratic form from E to F.
Where you don't have there is non-degenerate.
Oh, that should be a condition that
not
I had
rank.
to state right at the beginning. I only look at
Okay.
quadratic forms. Oh, sorry. Yeah. Yeah. Okay, so let's now discuss what we can else look at for finite fields. So what can we further ask for finite fields? Here, it is also interesting to compute the number of cliques of maximal size. This is another question to consider. So the number of maximal cliques, and here we can just use group operations to find the answer. So we have already seen the cliques and the subspaces that are generated by the elements of the clique heavily depend on each other, and thus, sorry. Can in fact be computed by considering the operation. So take the vector space acting as translations and combine that with the linear maps that are asymmetries of the product form. So we allow an asymmetry of the quadratic form and combined with some translation of vector space. This acts on V just by, okay, sorry, not on V, but on V times K for K.
This is now, I mean, this is the semi-direct program,
yep.
And you say, so if we should understand V as translations, and then this group really acts in this way.
Yep.
Yeah.
Yeah. So this acts as translation, and yeah, just applying the linear mapping to this one, this semi-direct product of these groups. This operates just coordinate-wise on this one, and when we specify it to k to the size of a maximal clique, then we can look at the orbit of some maximal clique. And indeed, we find out that there is an orbit consisting precisely of all maximal cliques. Yeah. So we know that there is an orbit that contains all the maximal cliques and no other subsets. Then finding the number of maximal cliques is equivalent to find the size of this orbit. So the number of maximal cliques is the size of this orbit, and this can be computed using the stabilizer theorem. So it's just follows from the vector space interpretation, so the generated subspace, if using some quadratic form results like this extension theorem of it. There's some things going up here, but yeah.
Over which field are we now?
Finite fields. We are still in the case of finite fields. So for an infinite field, you clearly have infinitely many maximal cliques because you can translate it everywhere.
What did you say just with the width extension result?
Yeah, to stabilize, to compute the size of the stabilizer of a clique. You look at the generated subspaces of two cliques. You have an isometry mapping the one clique to the other, and the extension theorem then show that you can extend this isometry of the subspaces to an element of this group over here.
Okay. Okay, then didn't know the extension theorem as such. What that name refers to? Yeah. Extension theorem.
No.
The fact that they all lie on the same orbit, this has nothing to do with the fact that the field is finite. Or doch.
Yes, it has something to do with it, because in finite fields, you can see that the cliques, the maximal cliques, are all of yeah, they depend to they live on subspaces that are really big. They have codimension 1 or 2 at most 2. So they are almost all the subspace, and therefore it's very restricted behavior. And so this one, unfortunately, works only over finite fields. And here I should mention, this is one point where we need this characteristic condition. There may be, in some cases, 2 orbits. The characteristic is 2. So you see, there may be other possibilities. Even for finite fields of the characteristic is bad. So, but there already was a little discussion during the break. The idea for characteristic is pretty much almost the same. There are some technical subtleties in the calculations, but all the approach runs through more or less, except for such small things that have to be changed. Okay, now I would like to talk about some further directions. So over the reals, you already saw it doesn't really depend on the A that is given. It just depends on the sign of A. And yeah, this has something to do that yeah, with the square class group of the field. So in fact, it will happen that many of the graphs for different A's are essentially the same. They are isomorphic and will lead to the same graphograms, of course. So if we have a quadratic form given for given Q, graphs for different A maybe isomorphic. So it seems like, yeah, maybe handling them together could lead to further insights. So we can talk about how can two different graphs for AA prime behave to each other. And yeah, in fact, there are combinatorial structures that are a little bit yeah, more complicated and contain more data than just graphs. So here, there's a combinatorial structure called association scheme. This combinatorial structure that both extends the theory of graphs in a way such that there are many graphs that that are built together to form an association scheme. On the other hand, these can be also handled algebraically, since I can, when I have given a group, I can associate an association scheme. Yeah. When I have an operation like this one, I can also build an association scheme. So many of the things that were given before, many of the tools, are put in together in these association schemes. They are at most, as I said before, generalizing graphs. And they in fact put together all the different graphs that can occur for a given quadratic form.
This is an honest scheme? Is a scheme in the
no,
that we know?
It's not a scheme in the sense of algebraic geometry. This is just a combinatorial object.
I thought you could have.
I have to disappoint you. So
You don't want to suggest that any other use of the word scheme is dishonest?
No. I don't want to.
Is scheming by definition not dishonest? Otherwise, it wouldn't be scheming.
So these objects also have further structure constants that in fact relate to the chromatic number as well. So ongoing projects will not only consider the graphs coming from quadratic forms, but in fact the whole association scheme, calculating these constants and yeah, looking what these constants can also say for the chromatic number. I did not divide my talk in two parts, two equal parts. So in fact, I'm done here. Yeah, that's what I wanted to say.